I'm going to remind you about some of the things that were studied in pre-calculus, but the emphasis wasn't exactly what's needed for calculus, and I've been trying to get people to change how they do this for a long time. Well, things happen slowly, I guess. So what we're going to talk about are the basic functions and what I call anchor points, which I'm going to explain. The idea is that there are several shapes that are the constituents of every shape that you're going to bump into using calculus. Well, almost every shape that you're going to bump into using calculus. It's kind of like when you learn to draw boxes and cylinders and cones, and then you put those together, and finally you get this really nice picture of your dog or something. But we don't have to be as complicated or as cute as a dog, but we do have to get some idea of what's going on. Once you have these basic shapes down, then you're going to use something that was studied, but again, not emphasized in pre-calculus, about sliding things around and stretching things or shrinking things. And the basic shapes will contain all of the stuff, almost all of the stuff that you have to do once you start sliding things around and the like. So let's get into the basic shapes straight away. The first one is the simplest one, and it's probably the most important one for calculus. It's a line, and so there it is. That's the line y equals x. Well, what about all this mx plus b stuff? No, all you need is y equals x, and then the ability to shrink and stretch and slide, and that takes care of all the mx plus b stuff. By the way, I hardly ever use mx plus b except under very special circumstances. In calculus, the right form is the point slope form, and I'll show you how taking those basic operations and applied to y equals x gives you all the other things. So the line is kind of simple, but I'm going to say that the anchor point is 0, 0. And what I mean by that is, if you take a line, to take this knuckle to be 0, 0, I can move it up, I can move it down, I can move it left, I can move it right, and then that takes care of, you just move the anchor point. So the anchor point carries the whole line with it. Where the slope comes into play is in stretching vertically, stretching horizontally. Again, we'll go into that in a little bit more detail. So there's the line. Anchor point is the origin, and if you move the origin to someplace else, you move the whole line to someplace else. And so there you go. The next one that has the equation y equals x squared is something that never seems to lose the interest of people who do math. This is something that people who do math, they start doing this before they study algebra, and they probably keep doing it, whenever, their whole lives, if you're doing math. So the parabola y equals x squared has an anchor point, the vertex 0, 0. And again, you take the anchor point, move it around, move it around, move it around, and that gives you lots of different places where the parabola might be. So, and there's some simplification with that. Okay, the next one, it's a little bit funky to draw, but it's the reciprocal function, y equals 1 over x. So I'm drawing the graph. This is not a real graph, this is a conceptual graph. But y equals 1 over x, and it's got these two branches. And of course, it's not defined when x equals 0. And I know that because that's how I got this scar in 8th grade. So now the anchor point is not on the graph. But if you move the anchor point, which again happens to be the origin in that formulation, you move the anchor point and you can slide it to the right, or you can slide it to the left, or you can slide it up, or you can slide it down. The whole graph goes with it. Even though the graph does not contain the anchor point is where the two asymptotes intersect, and the graph is asymptotically the asymptote. Yes, that makes sense. Okay. The next one is something that might be a little bit of a surprise for you, because this course does not have a trig prerequisite. And that's the fault of someone who redesigned the course a few years ago. It was me, and I made a mistake. But because when we're doing modeling, when we're trying to take something that's periodic and describe it, and we see that in the data, and we want to find an active function to describe that data, well then sine is the best thing we've got. And so we don't have to study all the ins and outs of the trigonometric identities and the dipsy-doodle homomorphism and the inversion and the inverse tangent to the cosine of the arc secant. We just need to know the function sine. You know it's important. It's built into a calculator. That's what you need to know about it. In fact, I'll show you later something that you can do that you can Google it. You just type sine of something into Google and it'll tell you. So it's not like it's a big mystery. There's a lot of interesting stuff that you can do with sine, but we don't have to go into that for the way we're going to use it. So let me draw the basic shape. It's the wave, and there's the graph. I should probably write down the formula. The formula is no help. It's like, what's sine? Sine's the thing whose graph is this. Oh, okay. The period here is 2 pi. And so what happens here is the graph starts at 0 and goes up, goes down, comes back to 0, and then repeats and repeats and repeats and repeats. And it also repeats the other way as well. So it's a wave shape, and so that's what happens with a lot of periodic things. Tides, hormones. Some people would like to see periodic things in financial markets so that they could buy at the bottom and sell at the top. But no one's ever succeeded in doing that. But man, a lot of people have put a lot of effort into trying. So stuff is periodic. In fact, almost everything can be described this way. And so there's the situation. I'm going to say that the anchor point is the origin. And I already drew it in another color, so I'll just circle it in red. And if you move the origin around, then you move the whole graph around with it, just like I'm moving the whole page. And there is a link to an older video I have for a trig class about how to do that. So I recommend that you look at that link. It's called graphing sine or something. Anyway, let me fill in some of the other points here just because they're important. And so there are a couple of points. They're not anchor points, but they're kind of determine what's going on. And so I'm filling in 3 points. One of the things about graphing is you don't want to do a lot of points. You only want to do the important points. And tick marks are just a complete and total waste of time. If you look here, I don't have any tick marks at all because I'm going to be moving things around, and that's going to be changing where the scale is. You have to indicate the scale, but you don't have to do a bazillion tick marks anyway. Okay, so our last known point is here. And so these are the kind of the key points of sine. The anchor point, when x is pi over 2, sine is 1. When x is pi, sine is 0. When x is 3 pi over 2, sine is minus 1. And when x is 2 pi, sine is 0 again. And then the whole thing repeats. And so there's the picture. And this is a very useful function for a lot of applications, which is why we're going to talk about it. It's built into your calculator. And there are a lot of fascinating things about it, like I said. But we just need to know there is a function that you have easy access to that models periodic phenomena. Okay, last one, and you're going to object, I hope, that this isn't a function at all. And so, but it's so useful and in so many things that I'm going to insist that we talk about it. And also illustrates this moving stuff around really well. So that's the circle, x squared plus y squared equals r squared. And let me draw the radius in here so you have some idea what's going on. So that's the circle. And again, if you use the tools that we're about to discuss, you can move the circle right, left, up, down, and you can also stretch it or stretch it, and so that's how we're going to do. So those are the basic functions. You've got their graphs, their formulas, and that's how a lot of mathematics gets done, is just by looking at the way these graphs act and get moved around. So, okay. So here's the basic principle about moving things around. And so you have a formula. Now, the formula may not be a function formula, but you've got x's and you've got y's, and you've got x's and you've got y's, and so forth and so on. Some people, by the way, like to write this. I'll do this in a different color. They like to write this hyperbola instead of y equals 1 over x, because that has the danger of dividing by 0. Some people write that as x times y equals 1. So again, those are the same basic thing. You've just multiplied through by x, but now you're not explicitly dividing by 0. And so, but you've got an x and you've got a y, and you can have more complicated things as well. We don't bump into those very much. You know what we bump into? We bump into parabolas. And so if you can master parabolas, you've mastered an awful lot of the tools that get used to understand what's going on in calculus. Okay, so two basic principles. I'm going to illustrate with the number 4, and we have, I'm just writing down two very simple things, x minus 4 and y minus 4. And when you subtract something from a variable, you move it that many units in the positive direction. So you move, in this case, 4 units positive. Positive y is that way. Positive x is that way. And so x minus 4 moves things 4 units this way. Y minus 4 moves things, whatever it is, 4 units this way. And so you can apply this moving things around to any anchor point. You do this if you want to, well, first, I'm sorry, I'm going to interrupt myself. Usually, we don't write y minus 4 equals f of x. We write y equals f of x plus 4. But so those are the same thing. They look different. It's the exact same values, but they have different interpretations, and that's part of being good at math, is understanding that that little switch can make things a lot more clear. Okay, so if we want to move the anchor point, I'm just going to pick out something as a place to move the anchor point. Let's just move it to the point 3 minus 2. And so let's see, I want to take this line, and instead of having it go through 0, 0, I want to have it go through 3 comma minus 2. That's the point slope form, actually. So what you end up doing is you're going to subtract 3 from all the x's, and you're going to subtract minus 2 from all the y's. And I wrote that wrong. My apologies. You subtract minus 2 from all the y's and 3 from all the x's. So, for example, the hyperbola becomes x minus 3 times y plus 2 equals 1. Or the parabola becomes y plus 2 equals x minus 3 quantity squared. Wherever I see an x, I now put in x minus 3. Whenever I see a y, I put in y plus 2. That's y minus 2 is y plus 2. And the circle is x minus 3 squared plus y plus 2 squared equals r squared. And so you could do this with any formula, but what you've done is you've moved the anchor point to the point 3 comma minus 2. So you can look at things when they're happening when the anchor point is the origin, you just slide it around. Okay, so that's the sliding part. The other thing is the stretch. So with the stretches, it seems a little bit counterintuitive, but so it takes some getting used to. 3x does something to x. If you take something with 3x, we'll show you what happens. 3y does something to y, and they both do the same thing. They shrink by, in this case, a factor of 3. in the direction. So 3x, you shrink it, instead of being 3 units, it's 1 unit. 3y, you shrink it, instead of being 3 units, it's 1 unit. So you shrink by 3 in that direction. So the most dramatic use for this is to look at something with the with circles. So let me illustrate this with circles, and then this is a tool that we can continue to use for the rest of our mathematical careers, not just for the semester. So one of the things that I can do is I'm going to take the circle x squared plus y squared equals 1. That's the circle with radius 1. And then what I'm going to do is I'm going to stretch it and shrink it. And so let's look at 3x quantity squared plus y over 5 quantity squared equals 1. So here's a formula that you might bump into. And so this is a circle, but it's been it's been shrunk in the x direction. And it's been shrunk by something less than 1. So it's actually been stretched in the y direction. And we can actually look at that circle quite nicely. It's an ellipse. The anchor point is still at 0, 0. But now instead of going out to 1, it only goes out to a third. And instead of going up to 1, it goes up to 5. So we stretch by a factor of 5 vertically, shrink by a factor of 3 horizontally. That's the formula. You can do a lot of algebra to make that formula less clear, but this is basically what's going on. So, basic shapes and sliding things around and stretching things. When you look at the point slope form, you'll see y minus the y coordinate of the anchor point equals m. That's a stretch in the x minus the anchor point. The slope talks about how much to shrink things horizontally. So those are the basic things that we can use. You can use this to graph a lot of things. It's not a precise graph. You don't want to use this to build a bridge, but you can get a very good idea of what's going on with almost every function that you're going to bump into by using this technique.